Akka. In production? All right, oh, good, good. About half, that's great. Okay, Akka-http is the topic of this talk. So when we got started with the predecessor project to Akka-http, we were quite surprised initially how much interest and uptake and popularity quickly developed around this tool that we had built. And it's an interesting question to go back and ask ourselves, like, why does almost everyone need a proper HTTP stack? Like, that's the reason why we have this amount of interest. And the core driver for this is the same driver as probably for a lot of the talks and sessions at this conference that you've maybe seen today and will see later. It's that our environment has changed significantly over the last years, as you all know. We now truly live in a multi-everything world, right? We are multi-threaded, we are multi-cored, multi-machined, multi-data centered, so to speak. It's multi-everything. That's the environment that we have, and that shapes the needs of the tools that we work with. And ultimately, all our applications are distributed. Whether we want it or not, there is not a single application that you can basically write today that is not in some way distributed. And I'm thinking about, concurrency in that sense also as a type of distribution, because it's distributed across threads and cores. That's like the most fine-grained type of distribution. But of course, we're also distributed across machines and data centers, across organizations. Essentially, our applications are distributed across the world, right? And there's no application that I have built in the last years that lived on a true island. It was always connected to some kind of other service, probably in another organization even, be it the Twitter API or Facebook or anything. But that's the environment that we're in, and that's the challenges that we face. And when we look at Akka, that you know, and you go to the Akka.io website, then Akka describes itself as a toolkit and runtime for building highly concurrent, distributed, and fault-tolerant, event-driven applications on the JVM. So that's quite a mouthful. So what does it mean? There's also a promise there that's a bit more catchy, and it says, Akka wants to make it easy for us to build powerful, concurrent, and distributed applications. That's the challenge that we face, and that's what Akka has taken on its shoulders, right? And the core points here are concurrency and distribution. When you think about a distribution a bit more, then distribution ultimately always means and implies integration, right? If I distribute something, I need to have a way to integrate it. If I can't integrate it, I can't really work with it. So, and within one machine, if we think about distribution between cores, then Akka gives us a tool to work with that, and that would be the Akka actors that you've probably worked with or heard of. Of course, there are many other tools that we can use to make that easier than 10 years ago when all we had were threads. But Akka actor is one module of Akka that makes it easy, right? And then if you go out one level, then between your own subsystems, meaning the systems that you control, then Akka also gives you a tool to make distribution and integration easier, which is Akka remoting and Akka cluster that you've maybe already seen. Especially Akka cluster is very interesting, and I'm sure we're going to see a lot of cool things coming out of that department or that part of Akka. And of course, we don't only want to integrate between our own systems, but we also want to integrate with other external systems that we don't control from other organizations, and that's where Akka-http comes into play, right? Because, after all, HTTP is the most successful integration protocol to date. It's what everyone kind of uses, everyone kind of falls back, and, well, it's not perfect, that's clear. There are lots of things that are kind of warty around HTTP, but it is there, everyone can use it, any platform, any library, any language somewhere gives you a tool to probably work with HTTP, and that's why it's interesting to us, because we needed to be able to connect our applications with the world. All right, so that's clear. So what is cool about Akka-http? Like what makes it special? Because there are so many different HTTP tools, toolkits, as I've already said. Now, the design goals behind Akka-http are, of course, as you would expect, It's maximum throughput with acceptable latency. We really want to use those cores. We want to scale. We need to give you something that doesn't get in your way, that is not slow. We want to be fast. We want to properly scale to basically unlimited amount of connections, unlimited in the sense of not limited by the toolkit, limited by your operating system or your memory, but not by any programming model, right? We want to use all the cores. And because it's about integration, it's not about only one side of integrating. We don't want to provide you only with a tool to work on the server side. We also want to give you a tool to talk to other services, from a client perspective. So it's about server and client-side support. So from the very beginning on when we started, it was always about having both sides. And it gives us actually nice properties if you model both at the same time, because they integrate properly and you can do things like proxying that we're going to get to in a second quite easily. And of course, it's to be modern, it's not really a framework, right? Not a framework style you might have heard already. It's a library that tries to stay on the sidelines and not kind of dictate how you build your application. You build your application with whatever you want to build your application with, and we just give you a library to solve this one focused problem, integrating via HTTP. And open composable APIs also make that easier, of course. And as I said, the focus is integration layers, machine-to-machine communication, mostly what we have in mind. You can use it for other things as well. The Spray website, for example, Spray.io website also runs on it. Of course, you can do something like simple web applications, but that's not the focus. If you're building an application whose focus ultimately is the interaction with a browser, then maybe you need other features like JavaScript, CSS, asset management, AJAX support, these kind of things, and then you won't find that in AKKA-HTTP, and then you might want to turn to something like Play, for example. Okay, that's the design goal. So what does it mean? If we follow these goals, what would the implementation of AKKA-HTTP look like? And of course, if we want to scale properly, we know we need to be fully asynchronous and non-blocking. We can't block, we can't be synchronous anywhere, because that will always hurt us in scalability. Then, because it lives on Akka, it's actor-friendly, so it's easy to integrate with actors, but it's actually already a step beyond that in a certain way. So the core APIs that we're going to take a look at later, they are not really actor-centric anymore. They are kind of their own thing. We'll get to that. And of course, lightweight, modular, testable, these are all the nice things that you need from a library like that. What is also cool, and we'll touch on that later, is that it's completely detachable. I don't know whether that actually is a word, decoupleable, maybe it is. I just put it on there. I probably know what I mean. It's like, it can be decoupled from everything that sits underneath, and you can take it in isolation and work with it, which is great. And as some of you might know, AKKA-HTTP is based on a library that's also already available, which is Spray.io. And that's been available for like 3-4 years and seen a lot of uptake. And the experience that we gathered from that is what drives some of the major improvements in AKKA-HTTP over its heritage that it got from Spray. Now, there's also a lot of stuff that we are very happy with in the existing world. For example, this is all what we take on. It's the nature of being embeddable, as you might expect, or maybe not. So it's, as I said, it's not a container that you put your stuff in. There's one nice thing, we'll also see that later, which is the HTTP model. So there's a proper immutable model for everything around HTTP. There is a very efficient HTTP parsing and rendering logic, which is one of the core reasons why Spray is so fast compared to other HTTP stacks. And it has a nice DSL on the server side that we'll also look at. And of course, it's fully integrated into the rest of the Scala world, so you use the same kind of configuration tools, debugging tools, logging tools, and so on, so that makes it nice to just work with. There are also a few things that we learned that weren't so great, or aren't so great in the existing Spray.io library. And one of them is handling of chunked requests. As you know, HTTP has all kinds of weird features, and one of them is chunked messages, where you don't send the message, request, or response in one go, but it's actually chunked. You can actually do something like streaming. And that's not that easy to work with. It's possible, but it feels a bit clunky. And we'll get to that. Dealing with large messages is essentially the same. If you have really, really large messages, then it can be a bit tricky to work with that properly. And the high-level DSL has a few rough edges that we can, smoothen over. Some things are just inherent to the Scala world and maybe trip up people that are new coming into Scala. They're not necessarily bad, but we can probably do a better way of documenting them, like implicit structures, for example. And of course, there are always missing features, right? Missing features will always be there. Currently, the most requested one is WebSocket support. If you go to the Spray.io project, there's a ticket for that, and there are like 199 plus ones. So you can just put yours next to it as well, and it will come. We'll also talk about that later. So there's one thing that I want to highlight, because when you look at those weaknesses, there's a common theme to the most important ones, the first ones, and that is the missing abstraction. We were missing a proper abstraction to deal with chunked requests and large messages, and it's ultimately about streaming, right? And that's something we'll talk about. And I want to highlight one example, one problem here, which is a real situation that we've seen several times. When you have something like that, you have a client and you have a legacy backend, and then people said, wow, cool, you have Spray, that's cool, we built a completely new service in Scala, it's excellent, it does exactly what we want, but we can't really switch off our legacy backend because we don't want to, right? It's for older clients, we just keep it running, and if someone requests something from version 1 of our API, we just proxy it over to the legacy backend, let the legacy backend handle it, and then proxy the response back. And because Spray and Akka-http, they both support server and client side, as I said, this proxying is quite easy because you work with the same kind of model. So this is what it looks like. A client would send a request to some resource, and the new backend built in Scala on Spray would just proxy that over to the legacy backend. The legacy backend would respond with a response. We proxy the response to the client. All good. Now you can probably see where we might have a problem here when you look at that. It's here. There's a risk of getting squeezed. Now why is that? Because if we're on the same LAN, 10 gigabit LAN as a legacy backend, but our client is in New Zealand and the response is really large, well, we need to somehow, somehow the client is the one who dictates the speed with which we can actually send the response, but the legacy backend will just, dump this large response on us through the network, and we're getting squeezed in the middle. So we need pushback. We need to somehow slow down the legacy backend, because I'm needing to spoon feed the client in New Zealand at 20K per second, and I can't take any, high bandwidth stuff. And that's, if you want to build this, it's possible in Spray, but it's not as easy. You have to do a lot of things manually, and it's brittle and not as robust as we wanted it to be. So there is something about streaming that we're needing. So what Akka-http does, it basically is the next version of Spray.io. It just builds on it. We do across-the-board polishing. We address those weaknesses like the one I just showed. We add Java APIs to everything, because Spray is just Scala only, which is nice for us as developers. But everything in Akka has a Java API, so Akka-http needs one as well. We simplify the module structure a bit, but there's one core improvement, one real important improvement, and that's that it's now fully based on Reactive-Streams. Who has heard of Reactive-Streams so far? Most of you. Okay. Who has a very good idea of what they are about? Okay, about 10 people. So, right, Reactive-Streams are its own big topic, and I like actually introducing people to that, but it's a really long talk. It usually takes like 2 hours to really go into it, and I don't have the capacity today. So today we just do it in one chart. That is all you need in order to be able to understand the rest of the talk. But it's a deep topic and it's great. And just check out the website, reactive-streams.org, to kind of read up on it. But what is it in a sense? The gist of it is it's an abstraction for asynchronous and non-blocking pipeline processing. That's what it is. It's about dealing with streams of data or streams of command or chunking up logic processing in a proper way. It's completely asynchronous. That's the key thing, because if you're not asynchronous, if you can block, then it's easy. But if you don't want to block for scalability reasons, then things become a bit tricky when you want to chop up pipeline processing in the right way. And the main advantage over prior works like RxJava, the old RxJava, is that it supports back pressure. Back pressure means exactly what we've seen before. If there's a stage that's slow and there's an asynchronous stage on my upstream where I get data from, I can kind of tell it to slow down in a nice way. And that works with Reactive-Streams, and that's all we need to make it really, really robust. And the idea behind it, there's a project called Reactive-Streams. If you go to the website, reactivestreams.org, you'll see what it's all about. There's also a GitHub page. It's essentially a standard API, a very slim standard API that you're not supposed to use directly as users. You're supposed to turn to one of the implementations of that API that gives you a DSL for nicely working with it. So you probably will mostly come into touch with Reactive-Streams through one of the implementations. And AKKA-STREAM, it's another module in Akka, is one of them. It's currently probably the most idiomatic one that you can use in Scala, the most mature one in Scala, let's say that. It has many, many use cases. It's a very general thing, Reactive-Streams. It's not in any way related to HTTP. It's a very general concurrency abstraction in a certain way. And it's a joint effort of companies like Netflix and Twitter. And when you think about what their business model is, you can probably see why they have a need for scalable asynchronous stream processing, right? Good, that's it, the gist of Reactive-Streams, that's all we need to know. Pipeline processing, asynchronous, non-blocking, fast, done right, and it supports back pressure. So when we go back to HTTP, where are we really dealing with streams? There are a few places. For example, if you have an HTTP connection, you can look at the requests that come out of that connection as a stream of requests. HTTP supports something called HTTP pipelining, which means that a client can actually send 10 requests in a row without waiting for the responses first. And that just means that you have a hose on the connection where the requests come out. And of course, the responses that you send out are also a stream. You can think about them as a stream. And the chunks of a chunked message are a stream. So I have a connection that has a stream of requests, and each request can contain a stream of chunks or a stream of bytes. So nesting streams is okay, just like it's okay to nest lists. You can have a list of lists, and you can have a stream of streams if you want. So these are the core places where we have streams in Akka-HTTP. Now this is an important chart. If you take away anything from this talk, it's this chart. Let's see what it is, what it means. It basically shows one HTTP connection, a client and a server, and it shows what you implement when you work with Akka-HTTP. And you implement the yellow bits. Let's look at the client. Suppose you have a processing pipeline that you define in streams. You don't have to, but that's a general case, that you have a streamed kind of processing where you say, first, I get my employees, I turn them into something, then I turn them in HTTP requests, send them off to some server, and I get back the response, and then I continue working with the response. And you write the yellow stuff, and what you get from Akka-HTTP is a component, a piece of pipeline, so to speak, that turns requests into responses. Because that's what a client does. An HTTP client turns requests into responses, right? So what we give you is a piece of hose that you can put into your pipeline that just does that. That's it. And you work with it. And on the server side, it's the opposite around. So you provide a piece of pipeline that turns requests into responses. Because that's what a server does, right? Turning requests into responses. In an asynchronous, properly scaling way, but that's what it does. So you, on the server side, you provide the yellow bit that connects the request stream to the response stream. Now what is cool about this? For example, if there's something slow here, suppose this thing is slow, somewhere downstream behind getting the responses, you have a component that is slow. So that means there will be back pressure, there will be stuff backing up here, right? You won't be as fast. And this back pressure will go through this connection through TCP, because TCP actually transports back pressure through its flow control mechanism all the way here. So if this thing is slow, it will slow down the server in being able to send responses. And because this is all built in a Reactive-Streams fashion, this back pressure will actually go through the complete processing pipeline on the server side, and it will slow down the client in actually being able to send requests, right? The back pressure through the streams abstraction gets propagated all the way to wherever it comes from. So whoever generates the requests in the first place this guy will be slowed down. So nothing will blow up here. The server will just properly kind of propagate the back pressure to wherever it comes from. And that is cool. And that solves the problem that we had initially with the backend, with the legacy backend. It'll just, through TCP, magically slow it down, and the legacy backend won't be able to overwhelm us at all. We can run in completely bounded memory at 100% CPU load, and nothing will blow up. Good. So when we actually do a double click on this, I've shown this as just one component, but of course there are several layers in there. So we do a double click on this. This is what the application stack looks like on both sides of this guy. Underneath we have, of course, the operation-specific network stack. Wherever you're on, if it's Linux, it's something else, it's something else. On top we have Java NIO that gives us the common layer to build on. We might actually in a later phase kind of circumvent that for specific reasons, but right now we sit on Java NIO. And then we have 3 layers that Akka provides. The first one is Akka-IO that already exists in a certain way, and the next version just adds a few more interfaces to make it a bit more, well, to add streamification, so to speak. What it does, it hides the ugliness of Java NIO, which can be hard to work with, especially if you need to do the threat management and all the concurrency stuff yourself with Java NIO. There are tons of ways to shoot yourselves in the foot. And Akka-IO does it nicely, so you just sit on that, that's good. It gives you TCP and UDP interfaces, message-based for actors, and stream-based in the new world of reactive streams. So on top of that, we sit with AKKA-HTTP core, which just gives you the small HTTP layer. Everything that needs to be there is in there, but not more. Just a basic HTTP raising and lowering level of abstraction. And AKKA-HTTP, there's also a model called AKKA-HTTP, a module, so to speak. And that module here contains all the higher level stuff, like the routing DSL and marshalling, unmarshalling compression, everything that you might want to use, but you don't have to. And you can directly sit on here, on this one if you want to. And that's what Play will do in the end. The Play framework will sit on here and not use this one. And AKKA-STREAM is the module that sits on the side because it provides the stream infrastructure that we need on all those layers. You can decide to use it yourself in your application, and I would recommend to, but you don't have to if you don't want to. Yes, one question.
On the previous slide, must both the left-hand side and the right-hand side be AKKA-HTTP for it to work?
The question is whether on both sides you need AKKA-HTTP in order for it to work, and the answer is no. As long as the other side talks HTTP, that's the beauty of it, everything is golden. And if I have an AKKA-HTTP client, but the server is Apache, then that's good. Apache is not asynchronous, is not in any way built like this. But it will, because it's synchronous, it will solve the back pressure problem as well. It just won't scale as nicely on the server. But that's the problem of whoever runs the server, right? So, and the other way around, it works the same way. The nice thing is HTTP gives us this common standard, and it isolates the two sides. AKKA-HTTP and Reactive-Streams just make it possible for us to build it in a proper way without blowing up, and with back pressure, and without limitations on scalability. Right? That's the nice thing. We can build it asynchronous, but not lose anything, or not, yeah, as opposed to the synchronous side. Good. It's basic. This is just what I just said. This is also what I just said. It's just a double click on this module and AKKA-HTTP as well. So let's just move on to this one in order to save some time. So we're going to show some. I'm going to show some code in a second, and there are a few things that you need to know about the AKKA-STREAM interface in order to be able to understand the code that I'm showing. It's very simple. So in AKKA-STREAM, it gives you a way to work with streams. And there are 3 or 4 concepts that we need to understand. The one is source. A source of T is basically the end of a pipeline, the end of a hose that produces elements of type T. Very simple. And on the other side, you have a sink. And a sink is just the opposite. It's the end of a hose that you just, stuff. It's like a terminator of a stream. It takes in T's. And in between, you have something called a flow, which is just a piece of pipeline that's open-ended on both sides, and it can take in A's, and it produces at its end, it produces B's. Pretty straightforward. So if you have a source of A, you can attach to it a flow from A to B, and that gives you a source of B, right? And if you have a sink of B's, you can attach to it, prepend it with a flow from A to B, and that gives you a sink of A. So that's how you can just plug those things together. The interesting thing is in akka-stream, everything is reusable, so you can take a source, you have an instance of a source, and that itself doesn't really do anything. You need to connect it with a sink, and then you need to push the button of saying, okay, go. That process is called materialization, and then this will actually create the stream in its real incarnation, so to speak, and run it. And you can do that several times in a general way. So if I have a source, I can attach a sink to it and call run. And I call run again, I get a new kind of incarnation of the same stream. Okay? That's all we need to understand. So let's look at this server API. The low-level Akka-http server API. What does it look like? So when there's a method called bind that you can call on an endpoint, which could be localhost 8080, and you'll get back a server binding. Well, let's actually take another example. Let's take port 0. Port 0 means you don't specify a port. Whenever you bind, the operating system will assign a port, one of the free ones for you. We use that extensively in testing. It helps. But when you call bind with an endpoint, say localhost port 0, you immediately get back a server binding instance. Nothing happens in this bind call. It just gives you a server binding. And the server binding looks like this. It has a stream of connections, a source of connections. So that means, what does that mean? It's a source where you can pull out at your own speed a new connection. So you decide when to accept a new one. If you don't pull anything out, nothing will be accepted. You are in control over when and how and at what rate connections are being accepted by the server. So, and this source is reusable. So you can materialize that several times. And if you bind to port 0, that will actually work, and every materialization will bind to a new port, right? It will just give you another server on another port. If you don't bind to port 0, if you say port 8080, for example, then you can only materialize it once. If you try to materialize it the second time, it won't work because you cannot bind twice to the same port. Okay, so the interesting bit is obviously, what does this incoming connection look like that I get out of this source? This is the incoming connection. It has, of course, a local address and a remote address, because by the time you have it, the connection has been accepted, and it's known what is the client on the other side. And then it gives us a few methods to work with, and we're on the server side. Remember, on the server side, we, from our side, from the application developer, we need to provide a piece of pipeline that turns requests into responses. And the way I do it is, I just call on this connection, handle with this flow. And that's the flow that I need to provide. Right? That's my responsibility. But I can give it the same flow. So if I build this flow instance once, I can take it and call for every connection that I accept. I just take this flow instance and say, handle this connection with this flow instance. And then the infrastructure will materialize that flow, so turn it into a running bit, and then actually power the connection with it. Plug it into the TCP connections and so on. It'll just work. And then there's a bit of sugar if you want to. You can just say, you know, I already have a function. It's a synchronous function that can synchronously, non-blocking, in a non-blocking fashion, turn requests into responses. Then you can just use that rather than having to create a flow around it, which is easy. It's just a map element of a flow. But you don't have to construct a flow map yourself. You can just call handle with a synchronous handler. Or if you have an asynchronous function, so a function that for any request gives you a future of the response, then you can also use that. No problem. Okay, that's nice. There's one interesting bit, which is what I said earlier about being able to decouple the HTTP layer from all the rest. Because the top interface of Akka.io is more or less the exact same API, just not for HTTP request and HTTP response, but for byte string and byte string. Because a TCP server is essentially the same thing, just turns bytes that come in into bytes that go out. And on the HTTP level, we turn requests into responses. So, and because we sit on top of it, we can actually give you a method that takes the flow that you provide, which turns requests into responses, into another flow on the TCP level, which turns bytes into bytes. And that's the essence of the HTTP layer, and it's completely decoupled from everything else. So you can actually take your server bit, the flow, call this method, and you get back a piece of pipeline that represents what should happen on the TCP level. Now, you can take that and actually plug it into the Akka.io API to have it run, but you don't have to. You could, for example, in your tests, take this flow and feed the bytes in yourself in a test to see how your server responds. And your server doesn't really know whether it's running in a test with manually fed bytes or it runs on an actual network socket that is connected to TCP. So for testing, this is beautiful because I don't have to bind to any ports or work with anything on the I/O stack. I can just, use my HTTP layer all by itself. It's cool. So what does it look like? I'm cheating here a little bit because I'm just calling a nice method to show you how small this can all be. You can just, if you bind, you can say HTTP bind to localhost 8080. You get back a binding, and then the binding has a bit of sugar, where you can just say start handling with its synchronous handler. But all this does is basically attach a sink to the source of incoming connections and just pull out everything. So whenever there's a connection there to be accepted, I just accept it and take and on this connection then I call handle with synchronous handler. That's it. So that's very simple. And this handler does, you can see probably what it does. It handles GET requests to /ping by sending out a response with the content pong. And for everything else, we just produce a 4.4. So very simple. Scala is great in that pattern matching type, if you want to. But that's it. That's a local HTTP server running. Okay, on the client side, it's almost the same, just the other way around. So when you want to connect to a server, you call outgoing connection to an endpoint, say google.com, and you get back an outgoing connection. You immediately get back an outgoing connection instance. Nothing has happened at that point. You just have this that you can hold on to. And it has a remote address because we already know what it's going to connect to, but the local address is not at that point known, but we give you a flow from request to response. That's the piece that I've been showing that you can plug into your own streams. And whenever you materialize your own stream, then this thing will actually go out and connect. If you materialize your own thing 10 times, the same flow will open 10 different connections to the same host. That's the reusability of this flow thing. And just as on the server side, you can again kind of take the HTTP part all by itself, just the other way around. So you give it an inner transport that actually represents the client on the TCP level, turning outgoing bytes into bytes that come in, and it'll upgrade that with all the bits and pieces that are necessary to do HTTP into a flow that you can use in your own streams. And once again, this is great for testing your client, if you want to. So let's move over away from the execution things that we've been talking about, over to the model that is more or less very similar to what you have in Spray if you've already worked with Spray. So since we're in Scala, we have this great construct called case classes, which make it really, really easy to give us a proper immutable data types. And we have modeled HTTP in its entirety, more or less, based on immutable case classes. So there are high-level abstractions for almost everything in HTTP. It's fully immutable. There's almost no logic in there because it's a model. And it predefines everything that you need to work with: status codes, encodings, char sets, everything. And it's open for extension, so if you have your own media types that you want to provide with your APIs, it's not a problem. So let's look at what this looks like. This is a request, what a request looks like. So it's a case class. You have a method. Now, every request has an HTTP method. Of course, since we're in Scala, it's properly typed, so it's not a string get or a string put. There's a proper type for it that models the HTTP methods. And for the URIs, it's the same thing. We properly parse URIs for you, so you don't have to do it because it's quite complicated, actually. If you look at the RFCs of how that needs to be done, we've done it. And it's properly typed in Scala. The headers have their own type. And we'll look at the headers in a second. Then there is something that we'll also look in deeper. The entity, which is the content of the request, has a proper type. It's called request entity. So all the entities of requests are of this type. And the protocol is just the protocol version. But you can see all of this is typed. There's no stringly typing. It's strongly typing, right? So on the response, the same thing. We have a proper status code, types. It's not an integer, it's a proper type. And then there's a response entity, and this extends from HTTP message, just like the request extends from HTTP message, which is just a common supertype. Because sometimes you want to write code that runs on both sides, client and server. So just a quick look at the URI. The URI has a scheme, an authority which is typed, a path, a query, and a fragment. So, and we have a proper parser implemented that is fast and just does what the spec says, because the JDK doesn't provide anything that's so recent as the RFC 3986, which is I think from 2005 or something. So that's much too recent for the JDK to actually provide. So the interesting bit, and this is also what changed over Spray, is that we now have a really deep model for the HTTP entities, because it's actually a bit complicated what HTTP provides us with. So we have HTTP entity, which is a sealed trait, meaning we define the complete hierarchy underneath it. There are response entities, there are request entities, and then there are body part entities, because a common problem in HTTP is that you want to deal with multi-part messages, which contain several things. Like if you have a form upload, for example, then the form bits will actually end up in different parts of the same thing, and each part is its own entity again, so it's kind of nesting. And we model that by giving you a body part entity. And then there is a universal entity that you can just use for anything. Now, if you're the astute readers, you will have seen this, which kind of looks funny. Why does request entity extend response entity? Does that even make sense? Well, it does. It just means that every request entity, everything you get in a request, you can also use in a response, but not the other way around. And we'll see why. That's why everything you can use in any message is the same as what you can use in a request. So these are the actual implementations. There are 5 different ways to have an HTTP entity. The first one is a strict one. So strict means I already have the data. If I have a string that I want to use for response, then I should be able to just use that. I don't want to create a complicated abstraction around it. I already have it. I know the content type, and I have a byte string in Akka, which is an immutable kind of sequence of bytes. I already have that, just use that. That's fine. It's a universal entity. I can use that for any entity wherever I want. But that's not the general case. In the general case, I have a content type, a content length, and I have a source of bytes. So I need to provide a hose that can provide potentially 100 gigabytes of data, and then that's fine. And I can use that everywhere if I know the content length and I have this stream. Now for chunking, it's similar. I have a content type, no content length, because chunked messages don't have a content length, and I have a source of chunks rather than byte strings. And these chunks I can produce in any way I want. So this is good for streaming. And I don't need to know how long this whole thing is going to be, because HTTP allows us to send it without that. Now I can use that not everywhere, but I can use it on requests and responses, but not in body parts. So inside of a multi-part message, I cannot use that thing because HTTP doesn't allow it, right? And we modeled it in a way that you can't do it. So that's what strongly typing is all about. And there's one thing that is only a response entity. And that's a feature of HTTP 1.0, the very early ones, which allowed you to send a response with a content type, no content length, and then just send, and terminate the response by closing the connection. That's allowed in HTTP 1.0. It's actually a crap feature that they realize it's not really great, because closing the connection is not really something that is clear whether the server actually intended to close the connection or there's a proxy in between that just closes it. And I have no way on the client to figure out, is that okay or isn't it's kind of brittle, right? So it's not recommended anymore, but it needs to be supported. And you can only use it on the response side, because sending a request and then terminate the content by closing the connection kind of defeats the purpose, because when I close the connection, how do I read the response? Right? So on the request side, this doesn't really make sense. So that's why we've modeled it in a way that you can't use it on the request side. You can only use it on the response side. And you can see that we've thought about this to give you a type structure that makes it impossible for you to shoot yourself in the foot and use the wrong thing on the wrong side. So this is proper typing. And down here, this is specific to body parts, so let's just skip over that. So exemplary headers, what do they look like? If you know the HTTP model in Spray, then that's the same. It's just a properly typed model for except charset. It uses the funky backtick notation of Scala because we want to make it easy for you to remember what's the type of the header for except charset, right? It's exact the same string, just in backticks. So you don't need to think about, is it now with an underscore, or is it just camel cased, or no translation step for you. Just use the header as you know it from the spec, put it in backticks, that's the type. And since we can't model everything, we also have an escape hatch for you to, so if you want to do stringly typed headering, you can still do it. A quick look into the server-side routing DSL. So it's a DSL that helps you to specify the API logic on the server side. It's type-safe and flexible, and it does actually much more than routing. So routing is actually a crap name. It consists of small building blocks called directives that are highly composable. The idea is if you have an application core that you write in any way you want, you put a REST API on the side, right? Not around it, it's on the side, it's a library. And if there's an HTTP request coming in, then the REST API should trigger an action in your backend. Your backend will reply with something, and that will be translated into an HTTP response. And the core thing is that the interface to your inner application core should be domain objects. So your inner application core shouldn't know anything about HTTP, right? You want to fully decouple that. That's how it's done. So just to give you the idea of how this works. So the API layer has the task of converting requests into things that mean something in the context of your application core, and the other way around. So the responsibilities of this API layer is, figuring out what kind of logic to run based on the method, the path, the query, the entity of the request. And then marshal and unmarshal. So serialize, deserialize in and from those domain objects. Compression is commonly important, right? That's something that we need to support. Authentication. Is the user actually allowed to delete all my database records or not? Yeah, that's something that the API layer should take care of. Caching, you always want to serve some static content. Of course, that's possible. And you want to make sure that your clients actually see proper error messages. That's crucial, and we take care of that. Because if you sell access to your APIs to some kind of clients, and they can't figure out how to use it properly, they're going to be frustrated, and it's going to hurt your business. So you want to make sure that if the client makes a mistake, they get as good error messages as possible. And we try to do that. So this is just an example of what this might look like. You have a DSL that describes what should happen when something comes in. So this piece is the same as before, right? You just describe the inner side a bit differently. And what it does, we don't really need to go into the details, but you can see we expect requests to /order/hex integer number to be either served with this if it's a GET request or this if it's a PUT request. And this means hex integer number is something that we provide, so you don't have to go through this trouble of figuring out, is that a legal integer? Is there an overflow? Is there anything? If it's not a legal hex integer, then the client will see a proper error message saying, status code 400, bad request. Your thing is not an integer, or your thing is not hex encoded. And this is nice, so you don't need to deal with that. There are lots of predefined directives, so small building blocks, that are available for you to compose. So let's go through all of them. No, we won't. It's just to show you that there is a lot of stuff already for you predefined. You just need to find the right one and combine it, and it probably can already do what you want, right? There's everything in there dealing with headers, dealing with compressions, character sets, path, query, whatever, right? So, good. There's a real-world example that I don't really want to go through, just to give you like an idea of what this looks like. So you can see that this is basically a tree structure, and you define on different levels, certain things. Lists, for example, extracts parameters, optional parameters from the URI. So you can have a question mark fixed equals 5, for example. If you don't provide that, then we'll take 0 for that parameter because this makes it optional and so on. So there are all kinds of things in here. This one is the inner side, and it says, okay, complete with this expression. If you know Akka, then you know that this is an act or ask, which gives you a future on the response, which is of this type. And the marshalling and unmarshalling is decoupled from this. It works through a mechanism in Scala called type classes, which sounds scary, but they're really not. It just gives you a way of loosely tying in this logic that you're not seeing here. So this is what it looks like. And this is one of those proxy things that I had. This is actually a sanitized client example. So they were actually doing this kind of proxying to their old Django implementation that they had. Okay, almost done. Best practices is just to adhere to architectural cleanliness. Make sure that you don't let your API leak in your application. Keep it separate, as we said. Use the unmarshalling infrastructure, and there's a small link to a tool in Scala called SBT Revolver, which can help you with fast development turnaround. Not much more. There's more that I could be talking about. There's stuff about testing. We have support of testing this kind of structure in a nice way. Client-side APIs, high-level APIs I haven't really shown. Then there's always a topic of JSON support and so more. What's the roadmap for Akka-HTTP? We're almost done with the core something. We want to have, by the end of Q1, let's hope, version 1.0 of Akka-HTTP out. You can already use it. It's available. There's milestone 2, I think, milestone 3 out right now. And WebSockets will come because Play needs it. These are the resources. The whole thing is online already on /sprayo/jfocus. So you can use click through if you want to. That's all I have now. Thank you.
Are there any questions?
Questions, anyone? We still have a few minutes left. Your chance. Come on, not a single question? All right. Ah, there's one. Thank you. Can you take the mic so that it's going to get recorded?
Does the back pressure introduce any sluggishness when you start getting, when it starts speeding up again?
Well, no, it does the right thing, but it's a good question. What happens if my server is at 100% load? Suppose I'm running full steam, red hot, 100% all the time, right? And there are new clients coming in. I need to define on my business layer what should happen then. Do I want to reject new connections because I'm fully loaded? Or do I just want to accept them and kind of degrade everyone, make it go slower a little bit for everyone so that I can still unload those customers? That's something that you need to decide, and we need to give you the tools to be able to express that in a concise way and actually make the implementation behave that way. That's what we want, right? So, and because you are the one to actually, or you can write logic to pull out the connections, you can decide yourself, you know, you're never going to accept more than 100,000 connections, or you're not going to accept new connections if you're running at full load or something. So the tools are there to give you that amount of flexibility, and that's great. So, and just, does it introduce sluggishness? It doesn't. As long as it's not at 100% load, it'll probably run as fast as it can. But when you are at 100% load, then it's about what should happen. And if you want it to become more sluggish, because that's what you decide for your customers, then that's fine, you can do it. Any other question? Thank you.
I think we had one question.
One question.
Yeah,
okay.
I think so.
Good.
You said there were Java APIs for most of this,
Yeah.
but I suspect that like DSL, the routing DSL, will be a bit awkward in Java. So how does that work?
A good question. So it'll look different, of course. Currently, the high-level DSL bit is heavily, centered around features that Scala gives you. So if we can't just translate that one-to-one into Java. That won't work. So what we did is we built a completely new, from scratch, DSL for Java that you can use. Of course, it's not quite as nice and concise as on the Scala side, but it's usable, and it gives you access to all the features that you have on the Scala side. So if you want to use it from Java, you can. And if you have any issues and some things don't work, please let us know, and we'll make sure to accommodate you, because our goal is to make it easy for people from Java just to use it in their language, because this is such cool stuff that there's no reason to just confine it to the Scala ecosystem.
Is it already released, the Java API?
Is the Java API already released is the question. It is part of the current milestone, so you can use it. I don't know how many people are already using it in production. I guess most of the users currently come from Scala. So it's bound to be not as mature as, other things in the Java ecosystem like Netty or something that that has a long time, for maturing and so on. So that's not where we are yet. So you're bound to find, holes in the documentation and maybe a bug or missing feature here and there. But the idea is you can use it right now and just run with it. Excellent. Thank you.
Thank you very much. Give him a big hand.